Good afternoon, all. Welcome. I know this is Sunday afternoon. It's a peak 2 o'clock. You guys had a lunch. Hope so. This presentation will keep you alive. Wait. Hello? I can hear. Hello? Yeah? Can you hear? Okay. Okay, welcome. So I know it's Sunday afternoon. Hope this P2MP will keep you awake. If not, I think there's no coffee. There's coffee there. So my name is Rajendra Chayapati. I work at Cisco Systems. And me and my colleague here, Utpal Mukhopadhyay in Cisco, we will be presenting today about P2MP. This will be introduction on P2MP. So we'll go with RSVP based P2MP and mLDP based P2MP. And we will be talking more on IPv4 based implementation. So if we have any questions or any clarification, feel free to raise your hands, and there's a mic in the middle. You can ask the questions. It's fine to ask in the middle of the presentation. And we would like to make it more interactive so that everybody's it's mainly tutorial. So it's a learning session for all of them. And some of this is a little bit of new technology, but not as new, it's not completely a drastic new technology. It's like an enhancement to a P2P kind of thing, MPLS on that. So in today's agenda, we'll start with the motivation. Why do we need P2MP? What is the reason? Why do we already have some multicast solutions working? What is the need to have a P2MP deployment on that? And with that, then we'll go with what are the multicast solutions available today and what is the upcoming multicast solutions. Then we will go with TE introduction. So basically the way we are formatted is to give you with the TE introduction to refresh our mind about how TE works and all that, because most of this concept is still applicable for point-to-multipoint. So we'll go with the TE introduction, then we will deep dive into how P2MP works, what are the signaling, how the labels gets allocated, and how data gets replicated and all that. Then we will go with P2MP sample config. Since I had an access to IOXXR config, I just put in IOXXR config, just to give you differences between what is the additional config you may need at the head end compared to P2P on that. So it should be similar to other vendors or even on iOS on that. Later on, we'll go with, again, same format as we'll go with the LDP introduction. Utpal will be talking about mLDP. So he'll give it, go again with LDP introduction. He'll give what LDP is and all, refresh our mind on that. And then we'll go with deep dive with mLDP on that. Then we have some references from where the RFCs and the acknowledgements of this. Then we'll have a Q&A at the end. So this is just if we have any additional questions, we'll take. So as I told earlier, we will have interactive, so feel free to ask any questions on basics on this or any of the implementation details. So in the motivation, basically why do we need P2MP? Right now the thing is we do know there are two types of service providers which is being implemented. One is the IPv4 based, which is the vanilla IPv4, and then we have customer service providers who are already deployed MPLS. Now it's almost more than a decade where MPLS has been already functional in most of the service providers, and they're already now more comfortable with MPLS in the core, and already the advantages of like L3 VPN, L2 VPN, and all that. So what all the advantages it provides, and they already deployed this in the network. So right now with the unicast, there are a solution where they can go with MPLS. Whereas for a multicast, if a service provider has to provide multicast, because nowadays with video being all transferred towards the IP, a lot of content providers and other customers are looking to have multicast also be part of their same IP network. With that, right now, if you have an MPLS network service provider, when they try to go to have a multicast, the solution right now we have is MVPN. So again, with the MVPN, the concept is you will have an IP in the core. Even though we call it as a multicast VPN, the concept in the core, the way the traffic flows is all through an IP layer. So it takes the unicast IP layer for using shortest path, and that is the control plane and forwarding plane for that. Whereas for your unicast path, it takes the MPLS path. So it's you will have two different control plane for unicast as well as multicast. So one of the things this P2MP is solving is to make sure that you have a same plane what you use for unicast, the similar one for multicast also. That way, whatever you have for your troubleshooting or administration, all that, it will be a unified single control plane for both unicast and multicast. And all the concepts of unicast still will be applicable to the multicast from a label point of view, distribution, and all that, OAM and stuff. Then the other one is in the existing multicast, you will, because it uses the shortest path first, you will not be able to traffic engineer in the network how the multicast path has to take. So it cannot take the non-optimal path. It has to go through the unicast path, unless you have to fine-tune the whole network using cost or IGP cost and other related factors. Well, if we go with the P2MP, which is based on MPLS, you can use the traffic engineering to route your traffic depending upon the need of the hour, I think in the early morning or in the evening and all that. You can kind of fine-tune it. And the last is you can also utilize the fast reroute capabilities. So whereas in the existing multicast, you have MOFRR, which is very, very recent, but still it do have its deficiency because you will be replicating packet twice in the core network, even though it gives the FRR capability, the MOFRR. But it is not synonymous with the fast reroute what we get with MPLS on that. So we'll go today the native solution. We do have the IPv4 and IPv6 is based on the native solutions. For an MPLS, we have the GRE based, which is basically the MVPN, and native multicast you can flow over a GRE based network. For a label based, in an MPLS, if you want to go pure label based network, these are the two upcoming solutions, which is the P2MP based on RSVP TE, and the other one is based on mLDP. These are the two solutions, and on these two solutions, you can carry any type of control plane, any type of packets, either it can be V4, V6, or MVPN, or 6P, 6VP. All this can be possible to carry on this. So today, in today's topic, we'll talk more on the IPv4 based multicast. So IPv4 based on RSVP and IPv4 based on mLDP, both using the label. Any questions? So these are the RFCs which refers for the P2MP, RSVP and mLDP. The RFC 4461, this basically defines the signaling requirement, how to set up the P2MP tunnel, and RFC 4875 refers to how this is being implemented in RSVP. This is basically an extension which has been done for RSVP to support point-to-multipoint. So with that, if you really see the 4461, if you go to the RFC, the main thing, it's similar to a multicast. A P2MP is similar to a multicast, it's synonymous. You can think of like you can say whenever a new node comes in, we call it as grafting. Whenever a new node goes out, we call pruning. So it's almost, if you know about multicast, most of the concept is similar in P2MP. You can kind of, a new node is joining in. That is basically it's grafting, how the grafting has to do, how the label has to be done, what is the traffic, whether is any traffic loss is expected in grafting or pruning. That kind of things. That's what been explained in 4461. And 4875 basically has the extensions which are done for us, the RSVP. So that way, the neighbors, when they talk the RSVP packets, then it knows that, hey, this is my P2MP, this is a P2MP type of labeling it has to do and all that. Then we'll go with mLDP. mLDP right now it's in a draft, this one, which Utpal here will talk later on in the session on that. Again, and one advantage with mLDP is it supports both P2MP and multipoint to multipoint. So we'll now go with the basic traffic engineering introduction. So in the traffic engineering, this is a point-to-point traffic engineering where you'll have, this is the terminologies we normally use is the head-end router, there's a midpoint router, and the tail router. So head-end router is where your tunnel is being originates. You can have one or more mid-end routers. The midpoint routers can be more than one. Here we have shown only one for just cinemas, but you can have multiple midpoint routers where the tunnel travels through. And the point where the tunnel terminates, that's called the tail end routers. So, and always the tunnel is a unidirectional tunnel, goes from the head towards the tail. So now we'll go with how does a TE tunnel get set up? What are all the messages being flown through across each of this router and how the tunnels get set up? So the first, when the traffic engineering is enabled and across the routers, they will be using the OSPF or IGP extensions, such as OSPF or ISIS. All these routers will know about the adjacent routers, link bandwidth, link attributes, capabilities, and creates a database called traffic engineering topology database. Each and every router in the network creates this topology database. So that way they know if the neighbor router or the neighbor across the network, how what are the links available, link attributes available, what links have been enabled for RSVP and all that. So this topology is created. Then once you configure the head-end router with the tunnel destination and all the parameters, the first tunnel head-end router will send a path message to the neighbor router, depending upon the way you have created the tunnel. This can be either a dynamic tunnel or dynamic path or an explicit path. A dynamic path is basically where you are saying that, hey, this is the destination. I will let the IGP decide how it has to take the network. So depending upon your IGP, it will say this is your next hop router, and each hop it kind of flows through, and that is dynamic. In an explicit path, where you can say that, hey, I want to take this via R4 or R5, a different path from, for example, from California to New York. Either you can go through Seattle, even though your shortest path can be through Arizona, right? So that you can define by using the explicit path. So both of these, so what happens is if it's a dynamic or explicit, the head-end router will send the RSVP path message to the neighbor router. And when it sends it, it will say, hey, this is the bandwidth I require, link attribute, and the tunnel bandwidth. These are the requirement I need, and it will send it to the next neighbor. The next hop router will look into its database and say whether it can satisfy the link attributes as well as the tunnel bandwidth. Does it have that enough information? If it is there, then he will accept it and say it will send back the accept message to the head end, and it will pass this path message to the next hop, who is the next hop of that or along the path from the head toward the tail. So this messages goes on traversing across each hop of the routers till it reaches to the tail end. Once the tail end, it reaches the tail end sees that, okay, it's accepted, this is the head, and then it will send back the path message, and then the label starts setting up from the head towards the tail. And once this is set up, this is where the tunnel LSP path is set up. And once this is set up, now the traffic flowing from the head to tail will take this LSP path, and the traffic starts flowing. So this is here an example which I just talked about. Here we'll see an example how this tunnel is getting set up between R1 and R9. So we here have two paths, R1, R2, R3, R4, and R9. That is the shortest path. And there's another path from R1, R2, R6, R7, R4, and R9. Right? These are two paths available. Now we'll see if there is a tunnel request coming in for 20 MB. So there is a 20 MB request, which is that where you configured a tunnel which says I need 20 MB link bandwidth. So from R1 to R2 it comes in. Now R2 looks into it. Hey, my next hop going to R9 is R3. But then it looks into that. Hey, my link is only 15 MB, whereas the requested is 20 MB. So I'll say, hey, I cannot accept this. So he will look into alternate path. For him, the alternate path is R6. He'll say, okay, let me start having this tunnel set up via R6. So then R6 is 60 MB and request is 20 MB. He will accept it and forward the RSVP message, path message to the R6. The R6 then looks into it. It has one link, 100 MB, that satisfies these to R7. Similarly, it goes up to R9. So once the R9 accepts it, it will basically send the receive message back towards the head, and then also associates the label to be used. Each hop gives the label. For example, R9 is the last hop. That's why it does a pop. And then the previous is R4, it allocates 32. Similarly, these labels are allocated towards the head end. Yeah.
In this case, R2 is making the decision that there's not enough bandwidth on that link.
Yeah.
What if the 40 and 15 around R3 were reversed? If R2, does R2 send reservation messages down both of them at the same time, optimistically, and say which one of you can satisfy, or does it just pick one of them?
Yeah, the question is whether R2 makes...
What if R3 were the one that had to reject?
Correct. Yeah, that's a good question. So if there is a, I'll just repeat the question just for users. So if by chance R2, whether R2 sends messages for both, even if it can satisfy, for example, R2 to R3 is 40 MB link, right? It's satisfied. So it first takes the shortest path. If it is a dynamic or if it is explicit, it goes to the explicit path. At that time, it don't even send to the alternate path, because you are defining how it has to go. In a dynamic, it says that, okay, R3 is the shortest path, whether I have the link, whether I have the enough bandwidth. R2 looks into the bandwidth capability. R2 says that here it sees that from R2 to R3, it is 15 MB. So it makes decision, it doesn't have that enough bandwidth, and it will take the decision and say it is not possible. In case if it goes to, if it is a R3 case, then the R3 will look into its own, because this link bandwidth is local to the router, right? Because between R2 and R3, it knows what is the bandwidth, and it makes the decision. Did I answer?
No. So to answer your question.
So R3 would reject it?
Yes.
And I can't
Yeah.
give you that bandwidth, and then what?
Then
R2
it,
would take the alternate path?
no, R2 will not take the alternate path, because the path message is, because the path is that, and there's where it doesn't have the bandwidth, and the tunnel will be down, and you'll get a tunnel information saying that I don't have enough bandwidth across the link.
So you won't search out another different better path?
Yeah, no, it won't go back and again start the loop. Yeah.
Hi. In basic RSVP, we just consider also the Zetter, right?
Yeah.
But here we only concentrate on the bandwidth. So why don't we include that Zetter factor here?
Yeah, that's what, just I gave it here an example of, this is an example. When I told that there is a link bandwidth and link attributes. So in the link attributes, you have different, like link coloring, you can have colorings on all different factors. And if you have that, it will look into all these factors, not only just bandwidth, and make sure that all these are satisfied before the tunnel gets set up. For example, if you link coloring, you have like 3 or 4, right? You have a priority, you have colored it across the link. You said that this is the optimal poles, suboptimal poles, and you have defined, right? Some pools you have defined, and when each and every hop routers look into it, it will say, hey, whether I have enough bandwidth in that optimal link or the attributes, right? Coloring. If only it's satisfied, then only the message gets set up. So this is how you can engineering your network depending upon all these criteria. And in this example, I just gave the bandwidth.
But the T-spec contains like 5-6 parameters, right?
Yeah.
So do we consider all those parameters?
Yeah, depending upon if you have configured it on the head end, it will make sure that all that is satisfied. Okay. Yeah, sure. Only in this case, I gave an example of bandwidth. So once that bandwidth is allocated, right? So all this now from the topology tunnel database, all that is now it will detect the bandwidth already being allocated. For example, if from 80 MB to all now 60 MB. In this case now, if there is a new tunnel, you are trying to configure it on R1, another tunnel, and then you want to say you want to set it up for 20 MB, another 20 MB. Now the R1 to R2 will accept it, R3, R4 will accept. When it comes from R4 to R9, it has only 10 MB. So it says, I cannot set it up. He will send a path error message towards the source saying that I don't have enough bandwidth, and the tunnel will not go through. Okay. Yeah. Yes. Yeah. Yeah. Yes. Yeah. Yeah, it can be. It's basically in an MPLS RSVP traffic engineering, the head end and the tail end can be between P to PE or P to P or PE to P anywhere, because it's the source and head can be any of that. You don't have to be from PE to P. Head and tail should no need from edge to.
Any notation.
In the MPLS core. Yeah. It means your here R1 can be either a edge router, PE, or it can be even a core router. You can originate a tunnel from a core and going to another core, another edge. The only thing is the MPLS needs to be enabled. RSVP needs to be enabled across all. Yeah. So that's the key. Now we'll go with the P2MP, because most of the point-to-point, the tunnel T information is applicable for point-to-multipoint. So in a point-to-point, we saw that there will be only one head end and one tail, but you can have multiple mid routers. Depending on how many hop it is going through, you can have one or more mid routers. Whereas in a point-to-multipoint, you will have one head end router, and you can have multiple mid routers. It can have one or more tail routers. So tail end routers can be one or more. So if it's synonymous to your multicast, where you have one source and multiple receivers coming in, so you can have multiple receivers joining into one source. Similar to that, here you can think of the head end is the single source, and your tail ends are your receivers. So, and the control plane mechanism used is similar to point-to-point. So again, the RSVP messages goes hop to hop and checks whether the available bandwidth, link attributes, and all that, and then says whether it's applicable, then only tunnel gets set up. So, and with this point-to-multipoint, you don't need to enable any multicast routing in the core. So the multicast can be only towards the edge or before where you start the head end of that. Till that time, you can have multicast. In the core of the network, it can be only MPLS based. And the other thing is the S-G or the multicast groups gets mapped to the tunnel. So wherever you are starting the P2MP tunnel, either it can be from edge or it can be a core. So wherever you start, that is where the mapping happens. This S-G has to go towards this multicast tunnel path. And then the last is where it shows how the topology will be. Next slides actually kind of give you a detailed topology view of how the PIM and the multicast, non-multicast core will be. So one of the few things with the addition of point-to-multipoint on the MPLS core network, there are new terminologies being used for that, because there is now branching, routing, and all. If you see, this is similar to multicast where you'll have. So the source router, the source LSR is the LSR where the tunnel starts. This is the head end router where you start the tunnel, where you have the tunnel origination. That's the head end router. It's called source, and that's depicted by S. Right? Then there's a transit LSR. The transit LSR is the LSR which will just take incoming packet and send it out on the outgoing. It is like a swap concept, the P2P swap. Here we call it as transit LSR, which is the X, referred as the X word. And then there is the branch LSR. The branch LSR is the LSR which will actually replicate the packet, which are actually where the incoming one packet is getting duplicated across two network, if you see in this tail ends. So that's called the branch, which is the B. And the last one is called the leaf LSR. This is the edge where it's actually the tunnel destination. This is the leaf of the network, so it's called L. With that, why we need all these different letters, right? We'll come to know because there are different way the path. We have a new concept called sub-LSP, because a tunnel, because you have one head end, you have multiple tail ends, right? How do you, because in earlier point-to-point, it always used to be one head, one tail, so it was one LSP. Now you have one head and multiple tail. So from your head point of view, if you want to know, there may be 5 tails, how do you identify? So each of them is identified by a concept called sub-LSP. So within an LSP, you'll have a sub-LSPs. And in this case, you can see there is a top sub-LSP going from head end router to the blue dotted lines. Is going from S till here. There's one sub-LSP, and this is the second sub-LSPs. So when that, and here all the terminology is being used, S to L, means from source to leaf, I have one LSP path, and we define that as S to L. There's another one is S to PL. The path from source to set of leaves, means if there are 3 leaves, the combination of that, we say, hey, this sub-LSP is combination of these 3, we do S to PL. Kind of it's a combination of multiple leaves, right? Then there is branch to leaf. Means, for example, in this branch, it is dividing into multiple. This is a B2L LSPs. It's just a terminology names when you refer that, hey, this is the LSPs kind of thing. Yeah. It will be different. We'll see. From the next slides actually talks about that. We'll just go there. So, let's go with that. Okay. This is just how the PIM-free core is. Basically, you have the edge router, PIM West. So where we are saying that you don't need multicast in the core. You need only on the edge routers. So this is where we'll see how the labels allocate and how the RSVP messages are flown through. So the P West in this actually sends that there are now you configure two tunnels, two leaves on that, saying that P North is your one leaf and P South is your second leaf. So in the P North, it will basically start sending the RSVP message towards the next hop, which is the P Middle, and then it sends both towards P North and P South. With the sub-LSP ID, if you see, there is underneath there is an ID which says that sub-LSP ID 1, sub-LSP ID 2. So basically the same RSVP message, but there are two RSVP message, path message goes across to the tail. And once the tail accepts, there is a reservation message which flows back. Okay. So when the reservation message flows back, it basically now here, the first one, the 201, P North is allocating, saying, allocate me 201 label, and he sends it to the middle router. And the middle router will now send it, saying that, hey, I will give 101 for this message. And then this reserve message from the P South comes to the middle router. He already has 101. He'll say, use the same 101 label and send it to that. So basically it uses the same label. So till the point of branching, it uses the same label, and the branch it kind of, it's similar to the ATM where VC merge happens and then you duplicate. But only thing you don't concatenate the labels. It will be one label. Yeah. It will be. Yeah. It's here. That's true. Here basically it's basically telling me to what label to be used when the traffic comes from the P West side. Use 101 and then replicate. So the traffic comes on 101 and then it replicates on 201 and 401. Yes. Correct. This is where we are. Yeah. So yes. So this is where if there's one more, yeah, there's a single traffic comes in. So traffic from C sides to P West comes in. P West will slap a label of 101 because that is a label being allocated from P Middle. Use this label. So only one traffic stream goes towards the data. From a data point of view, it is only one traffic stream going to P Middle. The P Middle will now replicate it. In this example, two, towards P North and P South. So he will replicate, and he will also swap the label from 101 to 201 whenever it's going towards the P North, and the traffic going to towards the South, he'll take it as 401. He basically replicates and puts these new labels and sends it.
In the previous slide, this could.
Yeah.
What are those IDs? Are those carried in any of the objects now, reserve message? Or?
Yeah, it basically sends in the RSVP reserve messages. In the path message itself, it puts. That's how it can identify the sub LSP IDs. So, for example, right, there may be a bandwidth node or the link may fail here, right? Only that particular link should be brought down. Only is the message, but it's still this traffic should still be flowing through. That's why you'll have an additional sub LSP. That's the sub ID. So it will be there. So that's why RSVP message wise it will be twice going on control plane, but from your data traffic plane, it will be one packet going in and it will split.
How these IDs are generated at the head node?
It's basically internal.
Okay.
Internal, it's based on the head end routers only. And from the label point of view, it still uses from the same unicast label point because the label is on the internal RSVP messages. It's internal to it's a standard there. How you can use one ID. You can have multiple also because if you turn on multiple leaves from same head end, it has to use the different IDs for each.
Maybe you'll get to this later, but is this process all dynamic? Can a new person turn on the workstation and join from the south or north, and will the head end build and destroy the tunnels dynamically, or is that not supposed to happen?
Yeah, that's a very good question. Actually, yeah. So whether we can have dynamically P's, dynamical P's can come in and join, right? If you see on the end, right? Yeah. After the tail end, it can come in, right? After the tail end, it can come in. But the only thing is, if you see, since it is based on traffic engineering and the tunnel, you have to configure the head end and the tail ends. So you say this is the head end. These are all the provider edge router, P edge router, where the edge of this P2MP, and you configure statically saying that these are all my destinations. So that is one of the thing with the traffic engineering is you have to say who are all your edge. Later on, when you come to mLDP, where you will see the other dynamic path. In this path, you cannot, because there is for example, P south, P north, right? If there is a P east coming in, unless you create from a head end, unless you create another, that destination as PE west, he won't create that path. But if the path is already set up, for example, in this case, from head end to the tail end, already the path is set up. Now, if there is an interested S-G receiver coming in, then he can join it, because already it is set up. The tail end will replicate it. If there is a second receiver or if it is a new receiver, he will send it to P middle will start replicating. If it is set up. If it is not set up, then you have to configure statically the new edge chart. Did I answer? Yeah. mLDP, you'll see how it kind of dynamically comes into picture.
So what is the session object contain at the head end?
Which one?
Session object in the partners is?
Session object, so the thing is, we didn't want to go in depth with that one. I think the next session, which comes, I think they have a little bit more in depth about the messages, detail about that. Right? Just don't want to put it here, so it's coming on that. So here is an example how the LFIB table, right? How the LFIB table basically is populated. From a head-end point of view here, the head-end router, P west router, will have the same LFIB as the regular point-to-point. Incoming interface is from C to P, outgoing will be your S0. So there's no difference on that. The main changes you will see is on the mid router, or where there is actually replication happening. So in this case, your mid router here, if you see the LFIB, your incoming interface is 101 is your label, incoming interface is serial 0. Then if you see, there will be actually 2 labels allocated and 2 outgoing interface. In normal case, it will be 1-to-1. Here you are saying that, you will see that in the LFIB, it says, I have to send on 201 towards S1 on interface, outgoing interface S1, and 401 outgoing on the S2. So basically here is where the replication happens, and it divides on both. So traffic flows through this, and then the mid router replicates it. So one of the things, if you see is in the multicast, the main thing advantage of the multicast is always it does the RPF check, reverse path forwarding check. So it makes sure that the traffic, whichever it receives, make sure that the traffic is receiving in the proper interface where the routes are supposed to come from. Means it makes sure that the source is coming from the same interface. So it does the RPF check. Now, with the introduction of P2MP and with the tunnel, your traffic is coming as on a tunnel interface, which is virtual interface. There's no physical interface as such. It's a label, and there's no mapping of label to the interface. So the way it does is there is a new concept called LSP virtual interface. So each tail-end router will create a called LSP VIF. So tail-end router will create LSP VIF for each head-end router, and it will be in the database. And this is where the multicast has also been enhanced to support this. So when the traffic is coming on an MPLS network and with the P2MP, and when the labels are swapped, removed, and it looks for the source of the stuff, it looks into the tunnel head, the LSP VIF as the RPF check. And then it will say, hey, accept this, this is coming from the right head-end router for me. And then it will forward the traffic. So this is a new change which has happened, and so the RPF check happens on this LSP VIF. So if you have multiple multiple tunnels from the same head end, it will have only one LSP VIF. So each LSP VIF is per head end router. So because it comes from the same head end where the source is coming from. So the next slides actually discuss about this, how it's being done. If you see in the topmost router, you have the RPF check. There are two sources, two S, Gs. Both are originating from the same router, router A, which has S1, S2. Both are two source and same head end router. So for both of this head end router, you have sub LSP1, sub LSP2. But if you see, there is only one LSP VIF gets created for both of this head. So, and then in this bottom is where you have only one head and one tail, and then it goes with one VIF. So it is the LSP VIF virtual interface is basically per head end router. So you can have multiple source on that. And then basically just saying that how the RPF is being through BGP next hop is how it is kind of identified who is your source, the head end router. Any question? Yeah. Yeah, that's what. Here, if you see, that's here there are two P2MP LSPs happening, but it's coming from the same head end. So this router, since it's coming from the same head end, it will only create one LSP VIF, and it will map for both of these P2MP. It will map to the same LSP VIF when it does the RPF check, just for RPF check. So otherwise it will be duplicate of head end for each one. So it creates only one. When it does the RPF check, it checks for that. So as I mentioned earlier, so this is just we had able to get an IXXR router. So this configuration is IXXR, but it should be similar to any other vendors or iOS. Here basically you're defining a tunnel interface, and here's the tunnel interface, and here you're defining multiple destinations. These are your leaves. You're defining multiple destinations under the same tunnel interface. This is how you identify one head to multiple tail. You can have multiple on that. And in this one example, we have given it, shown it is an explicit path. It can be dynamic. Just we are shown here as an explicit path. They're saying how the explicit path is. So you can have an explicit path per destination, how it has to flow through. So and then here is the we are given straight, and it has to go through 1112, and this also goes to 1112, and the 1112 router differentiates towards 1122 and 1333 kind of. So till this midpoint is where you're saying the same, and then branch it into two.
But there are, it says path option 1, so you can have other path
Yeah.
options as alternate path.
Correct. As a regular. Yeah, sure. Yeah. So you can have path option, and you can have path option 2 different, multiple. You can have as default final, you can have it as dynamic. If everything doesn't work, go to dynamic. So from then RSPF, OSPF and RSP and traffic engineering point of view, there's no difference between the regular point-to-point traffic engineering interface versus point-to-multipoint. So you basically enable the MPLS traffic engineering on this one, on the area where this basically enables the OSPF for the IGP extension. So that way now when it will talk to other router, it will know about from using the opaque LSA. It will kind of exchanges the link bandwidth and attributes and all that. And how it creates the TE database. So it's basically you've done here. And then basically you're saying on which interface you want to make sure the traffic engineering RSP message to be sent. So which interface, you can have multiple, but this is the interface where it's sending the RSP back. So and this is basically, this is again MPLS traffic engineering on this 10 gig interface, you're enabling it. It's the IXXR implementation. So here is the, from the output point of view, show output point of view, how it's being, how the head end router and how the mid router will showing. So in the show MPLS following, it's basically saying is the incoming, the local label is 21028. It's the head end router. We don't use towards the CE, but if it is another P router, it will send this to the next hop router. And this is the 101 is the label to be used when packet goes out, and it's going on 10 gig interface on that. So if you see in the branch router, this is where you will see the replication stuff. Where you're saying that your local label is 101, this is the one you passed on to your head end router, this is the middle router. And then you're saying that now use 201 when going on T interface, this one, and then there is 401 going on this interface. This is the way it's basically replicating. And it keeps counter for each one, and you can know that it's branching happening. Yeah. Yeah. Okay, it's a very good question actually. This is where on the tail end router, whether it is needed to have penultimate hop popping router. Basically, since the RPF check is happening on the tail end of the router, if the popping happens on the earlier router, the tail end router will not know about the RPF. So that's why in a P2MP implementation, there is no PHP. So PHP, we cannot, there is no PHP concept. So the label gets popped only on the leaf. So that's one change. Yes, that's a good question. Yes. So that's why you will see the label going here. So the label only pops on the last router because of the RPF check. So here is the again from the TE midpoint configuration. Again, in the TE midpoint configuration, there is no difference from a point-to-point configuration point of view. You are saying in the OSPF, what all you need is the same, similar to the head end where you're saying that you're enabling the IGP extension, saying that which area the NPLS is to need to flow through, and then you're saying which are the interfaces, and you're basically enabling MPLS stuff. This is on the mid-end router. So in the tail-end router, again, the difference again is only in the multicast, where you're saying is which type of core protocol are you using on that. This is a new announcement where you are saying that on the multicast, saying that, hey, I'm using SSM-based RSVPT is my core tree protocol, because your core is not running MPLS, is not running multicast, it is running MPLS. So when the packet comes on that interfaces, now the tail end needs to do the RPF check, and to tell that to the router that, hey, look into the RPF via the LSP VIF, you are saying this year you are trying to say that you are enabling that. Otherwise, by default, multicast will look into the incoming interface depending upon the SPF path. So on that. So the last from the point-to-point, point-to-multipoint T is basically the FRR. So first, one of the advantages you get about the using MPLS for multicast is you get the inherent benefit of fast route. First, basically, if there is a link failure or a node failure, you can have an alternate path with the minimum loss of 50 milliseconds, below 50 milliseconds. So the backup path, when you configure a backup for either a link or a node protection, this backup path is similar to a point-to-point, and this backup path can only be a point-to-point tunnel. It cannot be point-to-multipoint, a backup tunnel. Backup tunnel should be a point-to-point. And this backup tunnel can back up either a point-to-point TE or a point-to-multipoint TE or a combination of both. So between a head and mid, or you may have already on that particular link, you may have already a point-to-point traffic engineering. And then you have enabled point-to-multipoint on the same link, and you are protecting it, right? You can protect both of this tunnel using a same backup tunnel. You don't need to define another backup tunnel. That's what it's basically saying here. Either this or a combination of both. So here we'll go with the point how the FRR works and what's the how the backup path works. Here in this case, the R1, R2, R4, there's the link, and we have protected R2 and R4. We have protected that. So if there is a failure, so if there is a link failure on this. Now, since there's a link failure on this, since it is already protected, there's an alternate path. You have defined that, hey, this is my backup path. So what happens is traffic starts rerouting on this alternate path. So this is where the link protection is, and you can have node protection, but this is a triangle. So link protection. So this is where you define it on R2. In the next slide, we have the config where you say this is the link and this is the backup tunnel. In the backup tunnel, you will say how the path has to be taken. So the failure rate not only goes to that path.
When you say backup, LSP, it's like bypass LSP?
Yeah, so basically what happens in the backup is when you define the backup tunnel, it already there is LSP created on the backup. And then when the failure happens, he will just use the same label, but use this backup path, encapsulate through the backup path and goes towards this guy. And when PE North receives it, he receives almost like he thinks that it's coming from the same, because the same label gets encapsulated and over this, and he depopulates it and looks into that, the same label what he's supposed to receive from here. So he,
receives a double label, two labels or what?
two labels, yes. Stacked.
So before the failure, R2 was a branch router.
Yes. R2 is a branch router.
So after the failure, does R2 send two copies of the data down to R3?
Yeah, because two copies. Because it goes as a bundle, because it uses the same label. From R3 point of view, it needs the same label. Yeah, it's two copies.
So temporarily, I'm sorry.
Yeah.
So temporarily, or even permanently, I guess, so R2 is sending the regular copy with one MPLS label toward R3 to pop.
Yes.
And then it sends another copy with stacked.
Yes.
Two MPLS labels.
Yes.
And if R3 pops one of them and sends it to R4.
R4.
And R4
Pops it out.
Okay. And that would just persist as long as the failure persists.
Yes. Because that is the path, alternate path, the backup. Yes.
But couldn't it also engineer a regular alternate path from R1 to R4?
Like, and then I couldn't get, the engineering means,
Well, from the branch. I'm not, couldn't it?
I mean, the thing is, because you're in the backup, you say which is the alternate path it has to take.
Right, but R1 has no knowledge that the failure occurred.
Yeah, R1 will not know that. Only the R2 will know that it's failed. And then that's where it will, already since you already have defined the backup, it would have already predefined that LSP path. The backup path is already, it's already would have been set up. When you define the LSP, that's where you guarantee the 50 millisecond, below 50 millisecond failure for data is because the alternate path is already set up. Only thing is it has to just swap it from that going on, instead of going on this, and put it on this backup LSP which is already set up. Otherwise, it may again have to send the RSPP message and again path setup and all that it has to go through, and you may not guarantee, because if there is, if after the backup you are starting the this backup path to be set up, if by chance there is no enough bandwidth or link attributes is not there, then you're basically you're not guaranteeing the SLA of 50 milliseconds and below. So what happens is, as soon as you define a backup path, that backup tunnel is already set up. Basically, make sure that the backup is up.
So you can ensure the 50 milliseconds at the cost of double bandwidth.
Yeah. Yeah.
Do you suppose both the per interface and per global label space out here? Per interface and per global space?
Yeah, for the label?
Yeah.
Okay, yes. So the way it's depending on the implementation on the vendors. Some vendors says that they want the labels to be on per interface level. So that's basically just how you allocate the label, how the MPLS will allocate the label. If it is a per interface, it uses on the interface session how many sessions you define. If it is a per platform, it takes all the interfaces into consideration and basically gives the labels on the platform basis. So it's basically how it's a vendor implementation details, but from working and the theory and the way the path setup and all, signaling is the same. It's just from which space you take. Either you take on a per interface, because per interface you allocate some labels, and in a per interface it uses the interface and the label as a combination. If it's a per platform, it uses router ID and the label as the combination for that. Yeah. Yeah. So again, yeah, in this case you may not need it. Again, a BFT has its own benefits, or like depending upon how you are. If you have multiple parallel links and you want to make sure only one link is you're trying to. Yes. Yeah. Yeah. Correct. Yes.
My question is, let's say we have BFD or
Yeah.
will detect the link faster compared to Rob's Oracle.
Yeah.
And the switchover, I know we have FRR. Will that add any significance or?
Actually, because even BFD again, it's dependent on the hello messages, right? Whereas in this FRR case, it's basically even below that layer called layer 1. Basically, your POS interface, as soon as it goes, it's way faster than your BFD. This is way faster than BFD because BFD again depends on hello messages and all that. So in this case, it is basically a layer 1. It's not FRR is not on the interface dependent. It's basically FRR. You're saying that if you, yeah, yes, correct. So, and the detection for the FRR in BFD, it basically detects and tells to all the routing protocol that I'm down. Kind of it gets to all wherever you're configured, right? Whereas in FRR case, basically as soon as the interface goes down, it will say that hey, this is down faster than it has to go to routing because it just tells to the MPLS. MPLS will switch over. So BFD will not add any benefits if there is configured, right? Basically, the link itself will tell to that it's failed, and the FRR will kick in from the MPLS point of view. Like UDLD kind of scenario, yes. If it's a UDLD scenario, BFD will, sure. Yeah, that case is sure. Yes, BFD will. That's a good thing. Where BFD will help in that. Different again, right? Routing protocol going up. So basically, here the FRR mechanism is whenever the interface goes down. Yeah. That it'll come back. So it's like sorry. No.
Not connected.
There's always something in, to have a break. Yeah.
So you're designing this application around multicast?
Yeah.
Video? So multicast protocols such as PIN, able to handle this fast read route? They don't have to recalculate RPF or anything like that?
Was that?
So PIN doesn't have to do any recalculation of the reverse path tree or anything?
Oh, no. Because the thing is, you have this LSP VIF, which basically you're saying the head and outer and how it is being, how it's has to check the reverse path. So since that doesn't go down in the FRR, it still has an alternate path. It says that, okay, this is already I have know this, and the BGP next hop will say this is how I learned it. Unless the head and outer goes down, that's the case where the LSP itself will be down and then it will fail.
But the trade-off is once your diagram comes back up here, is that you're basically effectively doubling the bandwidth.
Yeah.
On that fast read route path.
Fast. If your backup path is the path where you already have an existing path going in this scenario where we showed, there was a backup path which was actually going on the same path where the primary path was. There was a replication happening. There could be a possibility where you may have a backup path without even traffic going, right? In that case, it will be 1. But in this case, it was shown that 2. That's why it will have 2.
And there's no option for like a pseudo branch route or anything like that, right?
Yeah. Is it?
There's no concept of like a partial branch route or anything like that, where this
No.
is a standard and can do the same business.
Yeah. There's no. Do you had a question?
Yeah. So I guess the trade-off is fast convergence versus bandwidth.
Yeah.
I mean,
Duplicate.
I know in my operation, that's gigs of video data. So, that would be the main concern is saturating links.
So yeah, the way if you design your network such way that if that alternate path is like your backup path or other path, then it's fine. If it is taking the original path, then it is, yes, there will be duplication for that portion.
No, just to answer your question, your backup tunnel, you can make it carry your another set of traffic on it.
Yeah.
So the backup tunnel, it doesn't have to sit idle. Backup tunnel, what you configure, sorry. The backup tunnel, what you configured, it doesn't have to unnecessarily consume bandwidth. It can be carrying some other packets, and it can act as a backup for the primary one. So then you are not wasting bandwidth on the backup tunnel.
No. Like for the FRR or just the regular case? Yeah.
Refresh message.
Refresh message is there. It's a regular RSVP refresh message which goes through, make sure that it's alive kind of thing. The head end. Each hop. Yeah, that's where you create the sub LSPs for you. Yes, there is. Yeah, there's one of the thing about P2MP RSVP is the scaling, right? Scaling is where if you have a huge number of PEs, there is the RSVP messages will be huge because you have to send RSVP for each sub LSP IDs, which is part of the head end. Again, it depends on the router's capacity, like the processing capabilities. Yeah, it's like, but again, it's all again depends on the capability of the router. If it's a small router and which cannot capable, yes, right? Yeah, there will be like, because it's all you're now only for the control message you're basically telling it that the head end is doing the replication, right? So basically sending.
One other question, one other answer to that. When you have a large number of traffic engineering tunnel, you can tweak the control plane parameters, like you can refresh message reduction you can do, or you can paste them apart. That is to save CPU on the router. Yeah, you can do that. And quite often in the lab we do that. When you have thousands of traffic engineering tunnel, and you are right, a lot of refresh messages will be, it will take a toll on the CPU. We can see CPU goes up. But there is a control plane tweak to do that. I mean, if you want to save some CPU. Both. That's a control plane now. Both iOS XR and iOS both supported. But those configs are not shown. It is depends on how many tunnels you are talking about. If you are 5, 6, you are okay. But we know some European customers, they have 200 PE routers and there are lots of traffic engineering tunnel. We recommend them as a best practice. You can do this.
Yeah. The sub LSP level, I think I may have to I'll get back. Just because I'm asking where you're saying that whether the sub LSP maintains all the sub LSP. Yeah. It passed through. Yeah, I don't think so, but I think I can get back. I'm not sure on that one. Basically, you're saying that for each sub LSP towards wherever it branches, whether it keeps states for all that, right? I may not, but I will check it out. And this is the where basically we are saying that how the tunnel interface is configured. Again, this is iOS XR, similar to other iOS, where you are saying that here you have the IP number tunnel interface tunnel T1, which is the backup tunnel, and you're saying MPLS traffic engineering, you're saying this is the interface which is being protected, and this is your backup tunnel. And this backup tunnel, you're saying how the path has to go through, right? So it's basically you pre-set up, and this is how the LSP gets set up before even the switchover happens. Okay. So now I'll pass to Utpal, who will be giving again LDP and mLDP overview on that. Thank you. Please.
Good afternoon. My name is Utpal Mukhopathai. I work with Rajendra and I work for Cisco Systems. So I will be covering the other half of the LSM, which is Multicast mLDP. Now, before we go there, let's refresh our mind. I think probably all of us know how LDP works, what is the level distribution protocol. So we'll just quickly go through some LDP introduction, and then we'll try to see what changes have taken place in the RFC to cater or to carry or to convey multicast traffic using levels. So level distribution protocol was defined in RFC 3035 and 3036. So what is LDP, level distribution protocol? This is a protocol to exchange levels. Why do I need to exchange levels? I already know IP routing. So assumption is I have the reachability of the whole network. I know how to reach in my MPLS core, each and every loopback, each and every link by virtue of running a routing protocol, OSPF, ISIS, or the IGRP. So LDP will guarantee that for every router where you turn on MPLS LDP, it will exchange levels for the prefixes learned through the routing protocol. So that means we can see there is a mapping involved. I have learned IP prefix ABCD from that remote router. Now I am going to announce level for that prefix, what I have learned from my peers, to my peer neighbor. And by virtue of that, every router will talk LDP and will create a level switched path. We can clearly see it's a kind of different approach than what Rajendra talked in TE introduction or an extension to that just now he covered. So that is called level distribution protocol. We need to learn, or we will build a level space for the prefixes already learned by virtue of routing protocol. Now, once we learn the levels from each other, then there is a level switched path created. From that path can be simplest case between two peers who talk LDP, just adjacent peers, or even remotely connected peer, with whom I have a IGP reachability. So repeatedly I am saying I have a IGP reachability, I know how to reach the remote router, then only I am building a level space. And finally, the most important part in LDP, what it does, it tries to associate or build a level with the prefixes already learned and which are sitting in the routing table. So what is the mechanism? Now, how do I do that? As I said, they're well defined in RFC. This is just a few important steps. How does LDP work? Step number one, in order to exchange level, I have to know my peer. So discover peers. How do I do that, my peers? I will send hello message using some UDP protocol port 646, and to some known multicast address 224002 or some known multicast. Every neighbor will do that. Now doing that, I am announcing I am available, I understand MPLS LDP, and I am trying to seek my peers. Now once all the peers started talking, then by virtue of some protocol already defined, they will try to establish a session. Now that session has to be reliable because we have to maintain the session. Now to have a reliability, we take help of a TCP and we take help of a port 646. It is also makes sense. So we start a reliable TCP connection with peers. And then what do we do? Once we initiate an LDP session with peer, we start negotiating LDP capabilities. Not the what LDP capabilities. I have to negotiate a lot of parameters with my peers. Do you understand this protocol version? Do you understand this parameter? Do you understand this APC? After we agree upon, then we'll start exchanging level and other critical information. They will build a level space. Then we'll have our level built, and then we'll start forwarding traffic. And once we do that, then the last step, we have to maintain and we have to manage. Manage means, well, my peer went down, he has to withdraw levels, these levels are no longer valid, kind of management operation on my part.
So it's very similar to BGP, except you discover your peers automatically.
By sending hello package. Hello
Once
package.
you discover your peers, the rest of it is like BGP.
BGP or even OSPF. Look at that, all protocols talk the same, right? And OSPF also will exchange hello packets, try to establish a session. These parts are very common. So
When
now,
you have parallel links, how many each session has multiple peers within?
yeah, good question. I'll come to that. Now, one LDP peer, one LDP neighbor, I mean, that's a router, right? You are turned on MPLS LDP on that. Now, he can have multiple neighbors, one situation, and he can have multiple links between the same neighbors. Okay. Question is, when I have multiple neighbors, how many sessions I will have? Multiple sessions. Every neighbor, one unique session. Every neighbor has a unique ID. Usually you configure loopback address of the router as a ID. So every neighbor has a unique ID. Good. That is one approach. And what happens if I have one neighbor but I have 5 interfaces between them, 1 gigabit, 1 Ethernet, 1 POS, 1 serial link, and something like that. Am I going to create multiple sessions for every interface? Some vendors do. That's called pod interface session. Some vendors don't. That's called platform. Even if you have multiple links, you enable the LDP on both of them, but you will have one session. Because I will allow one session between you and another neighbor, just even if you have multiple neighbors. So it depends on the different approach, a different vendor. Does it answer your question? Okay. Now the most important part, how does LDP do that? LDP will exchange LDP message. LDP messages, what kind of messages? Remember, I am trying to set up a session, I will send hello message. I have already established a session, okay, I don't have to send hello now, let me exchange level information. So I have a message called level mapping message. I will try to tear down a level, I have another message. So everything is happening between the peers by exchanging messages. Now, how does the message look like? Messages carry information in the form of, very easy thing to understand is TLV, type, length, value. Why they are very easy? Because anytime you come up with a new protocol, you can say, hey, I will extend this new TLV, this is my new extension, type will be this, length will be this, value is this, pack it in a message, send it to your peer, ask him, does he understand that message? He can take 2 actions. I don't understand. What do you want me to do? Shall I forward to my peer? Yes, go ahead. Or, I don't understand. What should I do? Drop it. Drop it. So there are 2 actions you can say. Sometimes P router understand more than P router. Then P router's role is pass the message on. Because I want my other P router, who is my buddy, to understand my message and create that negotiation. So I can have a different role. Now the best way, easy way to do that is to take help of TLV, type length value. And type length value, you can see RFC has, IETF has come up with an RFC where they foresee that this kind of requirement will come in future, and you can come up with a new protocol. Okay, this is a new TLV for this new feature. So you can come, and that's what is happening. Why I'm insisting on this, when you come to mLDP, that's what they have done. LDP, they have extended by new FEC TLV, by new, not level TLV you already understand, but at least FEC TLV. Now, what is FEC TLV? As I said, in case of a unicast, it's a mapping between the level and the prefix. Because I said I already have the routes. I have a routes for 1.2.3.4, and I have to create a label for that. So you can say in a crude form, a mapping between 1.2.34 will have an associated level 25. That's called FEC kind of messages, or FEC TLV. So this is an example how the control plane angle it happens. So this blue line is my MPLS code. Okay. So who are the routers should talk LDP? This guy, P north, P south, P middle, and P west. Okay. So in case of a point to multi-point or traffic engineering, you saw that Rajendra said I will set up a traffic engineering tunnel from here. In case of LDP, no, I won't do that. I will turn on LDP here, LDP here, LDP here, LDP here. What will happen now? He will try to establish a session between them. He has only one peer. But this guy, P middle, has 3 peer, one here, one here, one here. So he will also try to establish LDP session between on the 3 peers. Now, once the sessions have been established using TCP 646, what will happen? They will try to exchange levels. Now, has he created already levels? Look at that. This is a short level table. Now, what does he know? Let's take this router. He knows how to reach 10 to 11. How does he know? Because it is his directly connected interface. Does this guy know how to reach 10 to 11? Yes. It is the IP routing table. He also knows. Because routing protocol is running in the core, OSPF or ISS. So he knows how to reach 10 to 11. What is his routing table will tell him? He will say, in order to reach 10 to 11, I will go on Ethernet 0. Fine. Does this guy know how to reach 10 to 11? Yes, he also knows 10 to 11. Again, for the same reason. Now, what is new then? Okay, now because LDP has been turned on, what it does, he creates a local FEC mapping or local level 20 for this guy. It is his route, and he creates on its own localized control level 20 for him. Okay. So far, similarly, this guy also created a local tables, I think 21, but I didn't show that, but 20. Now what happens, as I mentioned, next critical state, they exchange levels. So look at his point. He created, remember P middle, he also knew 10 to 11, and he created on his own level 16. He created on his own 10 for 11 level 17. But so far it is not working because, okay, I created level, what do I do with that? Unless I learn from my downstream neighbor, how do I switch packets using which level, I can't fill up. This box is empty. So what happened when he forwarded the LDP message to him, he filled up this portion. He said, yes, 10 to 11, now I have a complete story. In order to go to 10 to 11, if I receive a level packet carrying level 16, I will switch it out with 20. Similarly, he also filled up, this side was empty, until this guy exchanged him the level information. So he says, I know my local level is 17, but I don't have any outgoing level. So he learned from him and he filled up this portion. Now what happens? When a leveled packet carrying level 17 comes to him, he doesn't even bother looking the IP address. He will switch. Just by 17, I know how to switch 21 and which interface to switch faster. This portion, he will switch it out.
Does this all happen at the same time in parallel? Like, does the central router build the table with the empty last column
Yes.
before it even receives it from the downstream?
Right, right. So similarly, he will also build with an empty list.
And he'll make label
He will,
41
yeah.
for him.
See, for him also, he created on his 41, but this side is empty. Now they all started extending and fill up the outgoing part. So beautiful. And what happened now? What will he do with 41? You can see that my local level is for use by the upstream router, not for me. So until I forward 16, 17 to my upstream router, there is no value. So upstream router fills up with his outgoing level. This is how exactly control plane works of a level distribution protocol. So what did you see? I created a routing table, and out of that I built a level table. What is the advantage? I will be switching faster. Is there a claim right? Maybe, maybe not, because you have additional work to do. You have to build a level table. Is it way faster than IP? We don't know that. It's controversial, but at least we know using levels we can do some magic. For example, you can do, Rajendra showed, in a traffic engineering using the level, I can route on a non-optimal path, and using the level I can do some other fancy things. But levels also expose some security hack. But anyway, we'll not go there. Okay. Now, this is control plane, how the levels are built. How do I forward my traffic? Okay. Forwarding will happen from this side to that side. Because if you imagine, action started happening this way, control plane wise. So level information started flowing this way, level information started flowing this way. Now when data comes, data, this is a source, and let's say this is a receiver, and this guy is trying to send traffic to a destination 10 to 11 or 10 for 11. C router does not understand MPLS because he is not part of the cloud. Okay, so he sends IP packet to him. P router, he understands MPLS. So then he has a special role because he is the first router in the direction of the traffic who understands MPLS. Now he thinks, let me not forward using IP. I have an MPLS path. Why don't I use MPLS? And how do I do that? What he will take, destination prefix 10 to 11, data is here, header is here, he slams level 16. This is the outgoing level what we built last slide. He slams level 16 with the data and sends it to him. What he does, this middle router does not look at 10.2.11. He thinks, okay, I got a level 16. Let me not look into the IP address. It will take long time, 4 byte. Do I have a level table information? Yes, I should switch it out, changing 16 to 20. Because he changes, so he has a special name called swap router or swapping levels. Because he puts the first time the level, this router is called push LSR. This is swap LSR. Now he also does, if you send packet for 10.4.11, what he will do, he will slam a level 17 now, and then it will come here. For 17, outgoing entry is 21, and outgoing interface Ethernet. So he will send this way. And when I reach the last router, now I have two actions. I think one of the gentlemen mentioned, either I can pop it out here, which is some vendors implement, or sometimes if you pop the level out, look at that, your responsibility does not end. You pop the level out, you make another lookup into the IP table, because you may not have one link, you may have multiple links, and then you send it. Or some vendors like Cisco implement penultimate hop popping, so he sends IP packet from here to there. Let's not go there, that's a different concept. So this is how data forwarding takes place.
So this is downstream unsolicited mode, or?
Okay, good point. Now, what you talked about, how do I propagate level? What is the mechanism of propagating level? Propagation of the levels, that's the control plane portion. This router thinks I don't have to wait for any signal from my peer. I have this level built, send it. Who cares? If that is the case, we call downstream unsolicited. Nobody asked me. I have the level table built. Why should I? Just like a routing table. Routing table also, it doesn't ask me, right? I forward the routing updates. Same way. So that's downstream unsolicited. Sometimes, some of the vendors or some of the routers, some of the MPLS mechanism, you ask for it, particularly in ATM-related ATM-based, then you call on demand. So I asked you, can you give me a level? We will see a kind of flavor in the mLDP where it will be on demand. Like, why should I unnecessarily propagate? Let the request come, then only I will send. That is called on demand.
Indeed.
Usually, if the LSRs are ATM switches, you will try to have on demand. Because ATM tends to run out of the level space. Right? You are using VPI, VCI. And if it is a IP-based, usually unsolicited. Usually. Okay. So, few things we learned. How basic LDP works. Now, what has that got to do with mLDP? Let's see the extension. So remember LDP, I tried to discover my peer, I tried to establish a session, I tried to exchange level based on the FEC or IP unicast prefix, and then I tried to say once the levels are learned, I have no problem for the traffic. Okay. mLDP, I have to support multicast, right? That's the requirement, that's all we are talking about. Okay. So what happened, I need to enhance the LDP capability. And to do that, there is a draft, already I mentioned, this draft allows you, in order to future enhancement of a special kind of LDP negotiation, please follow this guideline. Okay, let's not talk that. Now, where do I extend? This is the new FEC element. Point to multi-point and multi-point to multi-point. We will not, for the sake of time, I am not going to cover multi-point to multi-point. That itself will take another 1 hour. I think there is a session after this. Shankar will be touching upon it. You will get more into know how multi-point to multi-point works. In order to keep synchronization with what Rajendra talked, point to multi-point RSVP TE-based solution and point to multi-point mLDP-based solution, I will touch only point to multi-point FEC. But my point is, how did RFC extend? Look at that. RFC had to extend LDP extension to take care of point to multi-point or to take care of the multicast traffic forwarding using levels. And again, where does the extension take place? LDP message. I have to send special kind of message with my peer telling him I am going to send multicast packet. And unicast level, whatever was prevailing, he won't understand that. You have to negotiate new FEC, new TLV, so those kinds we will see now. Yeah, look at that. This is the mLDP FEC element. Now, I did not show LDP FEC because I said kind of talk through that IP prefix gets mapped into the LSP and all these things. If it is a multicast LDP, okay, I need to build a tree. So what are my choices on the tree type? I have a point to multipoint, multipoint to multipoint up, multipoint to multipoint down. This portion I am not going to cover. So I need an address family, I need an address length, root node address, opaque value. These are all extension. Again, using TLV. This is the type length value. This is a typical extension. Almost every RFC you will see. Whenever there is a new requirement, they try to extend. Okay, new TLV is defined. So how does it work? Now let's come to the difference. In case of a RSVP TE-based solution, what he covered is configured on the root node. He is building a tree from the root all the way to the leaves, where the receivers are sitting. In case of a mLDP, it happens exactly the other way. Receivers initiate the tree. From the last point, it starts looking after where is the root, where is my source, okay? And then it starts walking. So this is the first point of difference. Egress LSRs or receiver, where in P2MP TE was the tail end, he initiated the tree creation. You can call it equivalent to multicast tree creation or by looking for the root address. Now root address, how will you know the root address? I am sitting far away, egress LSR, how do I know the root address? Either you let him know by BGP next stop or you make a static configuration, okay? So that means I am telling the receivers where the source might be. In one of the ways is when you define PMSSM, he will know S, G, where is the source is, okay? Now, I need to propagate from the leaf all the way to the root. So I need collaboration and cooperation from each LSR in the path. Because last router, then last but one router, then I will start walking all the way to the root where the source is. For him, he configured at the source and then he walked to the tail. For mLDP, I start from the end and start walking to the root. So, like anything, I need to discover what is the FSC and all these elements. So two types of signaling are defined. In-band signaling, out-of-band. Most of the, for now, I am restricting myself to in-band signaling. We'll see what does in-band signaling means. Okay, so this is the, more or less what I walk through, this is the flow. Upstream control plane signaling towards the root. From here, I am walking all the way to the root. From here, receivers are here, I am walking all the way to, I am looking for the root from here. Okay, this is how starts flowing. So receivers are here. He started sending level 201 targeted type is point to multipoint. It's not multipoint to multipoint. How is he sending? Using label map message. We just now saw that when we exchange with peers, we use a lot of mapping messages, a lot of messages. One of the messages level mapping. We talked that. So he is using that TLV level mapping message. Type P2MP. We saw the chart that one of the options is P2MP. Where should I go? Look for the root. Where is root? PE West. Okay. Where does it go? From here to here. That's it. From here to here. So it's a peer driven. So from egress, it says use 201. If there is a traffic for a point to multipoint LDP based traffic, use 201 to come to me. Now, this is where, to answer your question, kind of on demand will come. He will, only when there is an interested receiver, then he will send this level out. He will not build unnecessarily all the levels and okay, go. Then when he receives that level, he knows somebody is showing interest in this peer. So let me propagate that information to my upstream neighbor. So that's a kind of on demand, but it's not like it.
Does the opaque number, the value 200 there, that represents the multicast source?
Yeah.
The SMG?
Yeah, this value is the unique ID.
Who made that up though? Which one of the routers came up with that?
Which one? This level or this?
The 200.
200, okay.
It's the same in all of them.
Okay.
Which one invented that?
Okay. No, good point. So basically, this is a unique ID for that particular S, G, and so what is needed? You need to map all your multicast traffic to a point-to-multipoint LSP. Agreed? Because otherwise multicast traffic will, it needs to map. For example, IPv4 I showed, I have to go ABCD, mapping level is 20. So similarly here, it is not ABCD, here is a multicast S, G is there. So he has to be conveyed through a point-to-multipoint LSP tree. If you look at this tree will be rooted here, lives here, rooted here, lives here. So every tree has to be uniquely identified because I can have multiple trees over it. So one is depending on if I have another S, G, probably I will have another tree. So those trees have to be uniquely identified, and the control plane, those numbers when you are exchanging levels between these guys, this is a control plane operation, when you are exchanging levels, negotiating parameters, they are coming up with that unique ID when the route was reached, right? So he knows now from me to reach the LSP, this is the point-to-multipoint type of traffic I have to handle, and I need a unique ID, so it's a control plane's job, or through the LDP message it got created. Does that answer?
Okay, but all of the routers in the path have enough information to generate the same one?
No.
For the same S, G. For that.
Or can they all have enough information to
Yeah.
know that same value?
For that S, G.
Yeah, exactly. So,
SMG and the header.
and the header. So, no, header is, he still, because he knows about the source, am I right? Now, look at the 200, he also created 200, am I right? Because he knows this is the source I'm sending. And this is the
Yes,
FTC route is PE West. I know the PE West. And remember in the previous slide I said, do I know my route? And I said BGP next hop or statically? Yes, I know. So I know my unique route, and I am having an S, G entry happening at me. So then I create a kind of unique identifier through this guy. Actually, this that 200 is a kind of, it's a tuple kind of representation. Yes. So yeah, so that made the uniqueness of that tree.
No, we will need to do a BGP lookup to find the closest way to the route.
The BGP is the next closest way to look up to the route. Yeah, it looks on the IGP, whichever is the IGP path. It can be either BGP or the next hop, right? You're talking about the source?
No,
The source doesn't have to be an IGP necessarily.
Which one? Yeah.
My source is not an IGP, my source is only a P.
Yeah.
So P will have to make a BGP lookup to find the closest way to the route.
no. If you are okay, let me understand.
Yeah.
If you are using BGP, then BGP does a recursive lookup through IGP loopback address of the PE router, right?
And then it goes to the next.
And then that loopback address is known to the IGP, and so BGP is next hop. BGP is, if you talk about, let's say, this guy is running BGP through this guy, not here. When you talk about BGP allocation, then BGP is, if he's a PE router, he's a PE router, he's a PE router. So BGP only operates between these three, am I right?
So actually my question is, right now we are running BGP in the core only to support basic multicast. If I use this scheme instead,
You
will
don't-
I be able to turn off BGP in the core?
Yes.
Yeah.
Yeah.
Yeah, I mean, if you turn off, BGP is not, that's why I said, even you can have a static way of letting the source know. BGP is not the only choice, one of the choices.
Yeah. For the P middle router, you don't need BGP. Yeah. BGP.
Like if you know, if you have used classical L3 VPN, L2 VPN, none of the P routers will know BGP, right?
It goes to the loop back address and then it kind of.
So he doesn't need to know. He is just a pass-through. So BGP only operates only among the PE routers.
So the opaque values are just discovered or they're configured? These opaque values, they're 200.
Oh,
The control plane.
this is a control plane operation, am I right? So the way FEC level and in case of LDP level protocol, mapping between FEC, IPv4 prefix and level happens. Same way, this is a control plane operation, FEC root is known and opaque value is derived based on the S, G entry, which will be and the source address. Now here we used, I think that is causing confusion. Here just we did not use the full tuple. I used 200, just to show that they are identical here, here, and here.
Yeah, but
It's
S,
dynamic.
G, how does the south know the north? S, G is mapped to 200.
S, G means you know the source of the, am I right?
Yeah, you know the source, but it's not like distributed throughout the network. S, G means 200, right?
No. Let's say he is joining PIM SSM, S, G. What does S means? Where is my source? Does this router know where is the source? Does this router needs to know where is the source? Does he know where is the source? How will he know? He knows the loopback address. How will he know? Because of a routing protocol running within the core. He has a complete, if you ping from here to the source, can I reach? That's what my assumptions was. I have a complete IGP running here. Of course I have a reachability. I know loopback address of this guy, everyone. So I know the source. And if a source is connected here, that is also known. Does it answer? No.
It's a control plane. Yeah, it's control plane negotiates and allocates it. The internal, the TLV part, it is part of the TLV, which is the control plane which kind of negotiates. It's nothing, not user confirmable, it's through signaling.
Right. So you have to let the router know that you are going to configure point to multipoint. Agree? As soon as you will say MPLS, what do you do in case of LDP? You said MPLS LDP. In case of these, you will be saying MPLS mLDP. So as soon as you turn on mLDP, then control plane knows that mLDP is being turned on. I have to generate new kind of LDP messages. On the interface, you don't have to do anything. You just enable MPLS, simple. On the global front, you just enable MPLS, mLDP. I think by default it is turned on. If you don't want it, then you say no MPLS, mLDP. So MPLS, mLDP, you can say kind of superset. I can handle both classical LDP as well as multicast products.
Second thing is, we're talking a lot about SSM.
SSM.
SSM. Yeah, right now.
Yeah.
SSM, you're moving the concept of random.
Yeah.
Yeah.
Correct.
And then this is a 3 or 4 routes knowledge, but there could be chances that when we have, let's say, the source or let's say figure the answers, we're in that we're trying to figure on it.
Yeah.
Yes.
Yes.
Your source can be closer to your receiver, more than going to the
Yeah.
key value.
So to answer your question, of course it will do. And that SSM, PIM SSM, where actually multipoint to multipoint is very interesting, where you will see a kind of PIM binder and all these things, where you have a kind of RP, rendezvous point, where it's called shared route, where the route will be sitting somewhere in the middle. I think probably Shankar will be covering it in detail. If you go there, it's very interesting. Unfortunately, my slide doesn't have it, but you are right, you will see a very similar analogy to what you see in RP. There will be a downstream point to multipoint, there is an upstream point to multipoint. Everybody is trying to reach a shared route, And then, no, I mean, this will remind you, oh, this is analogous to that RP-based multicasting or beams per mode. So exactly it happens that way, and for which you saw the special allocation of the type point to multi-point up, multi-point to multi-point up, multi-point to multi-point down. They were reserved for that.
I think we might go fast. Okay. Yeah, it's already done, I think.
Okay, I think just
So a little bit, yeah, faster because I think the time.
time is running out. So basically, once you build this concept is similar, am I right? 201 came here, 401 came here, 101 came here. That's we borrowed the same label just to show similarity with point to multi-point RSVP. And then you just send downstream traffic, and that's it. So data comes S, G, and it's the same model, what you just now saw with that. And finally, I think that's all. So just to conclude, what did we learn today? We did not cover one important aspect of the mLDP, which is multi-point to multi-point. It was, time was not enough. Already we ran out of the time, and I did not have slides for that. But that's a very interesting and very complicated way of handling multicast. But motivation came basically what Rajendra started. If we offer multicast, try to offer multicast services to the MPLS-based service provider, they want to offer, they have no choice today but to re-engineer their core, to have one thing taking care of unicast, another thing taking care of multicast. Number one. Number two, you have to enable PIM within the core. Even if you are talking about MVPN, you have to go and enable PIM, you have to configure multicast routing in P router, in PE router, in all the P routers, which is hassle-prone. Secondly, if you have a traffic engineering tunnel doing excellent job for carrying unicast traffic, if you try to enable multicast, traffic engineering tunnel doesn't want to carry PIM traffic end to end, and a lot of messes happen. So again, you have to allocate separate link for carrying multicast packet in the core. So re-engineering the core, not being able to use traffic engineering, not being able to use FRR makes multicast traffic services a little bit problematic or non-trivial. So looks like this solution which RFC came through, where you turn on point to multi-point RSVP TE-based solution, where you use the same concept, only thing little bit of extension of point to point T to point to multi-point T, or LDP to mLDP, we can offer the services. That was the prime motivation, and we can have all the resilience and reliability and everything. Thirdly, where do we use what? Okay. Multicast we are talking, you want to distribute content. COS broadcasting, all employees are receiving content distribution. RSVP-based T, excellent solution, because only one source, a lot of receivers. When it comes to telepresence or video conferencing, when everybody is talking to everybody, looks like point to multi-point T has a problem. I have to really be clever enough to configure a lot of point to multi-point T. But mLDP-based solution, multi-point to multi-point, which I did not cover, is an ideal choice for telepresence and video conferencing. So that, with that applications in mind, I will close the session. Any questions? MP2MP. You have to be, I mean, you can make use of it, something like instead of point to multi-point RSVP T, can't you achieve with unique point-to-point T? Yes, you can, wasting bandwidth, all right? If you have 1,000 endpoints, I can create point-to-point T to 1,000 guys. And still guys. The middle guys, you are exploring the bandwidth. So point-to-point, multi-point T will solve that problem, because he is replicating only at the branching. Save the bandwidth. So everything has a solution, cumbersome solution, not a very good solution. Yes, option is there. I did not discuss it.
Yes,
but yes.
Do you have any experience with the multi-vendor networks, or is this just a
No, I know for
P2MP, RSVP TE, yes, we have worked with at least the multi-vendor has been okay. Because both vendor already has implemented and we have tested it.
Cisco has it, I think Juniper has it.
So we're testing. Yeah. P2MP, because mLDP is, as we pointed out, it's in the draft and
still
it's
in
kind of,
draft
it's in the
stage.
work in
RSVP.
progress kind of thing. So whereas RSVPT based P2MP is already there, means it's available in the lot of, at least Juniper and Cisco, it is there in the code already released FCS.
Any more questions?
Okay.
Thank you.
Thank you all.
Thank you all for attending.
Yeah.